Unit 1, Part 3, Probability Basics, a tale of two interpretations. Probability can be viewed through two major lenses, frequentist and Bayesian interpretations. Frequentist interpretation sees probability as the long-run frequency of an event occurring after many trials. For example, if a fair coin is flipped 1000 times and lands on heads about 500 times, the probability of heads is estimated as P of heads is equal to 0.5. This approach relies purely on observed data without considering prior beliefs. Bayesian interpretation treats probability as a degree of belief that can be updated with new evidence. For instance, a doctor might initially believe there is a 30% chance a patient has a certain disease, which is prior probability. After receiving the results, the doctor updates this belief using Bayes' theorem, which combines the prior knowledge with new data to form a revised posterior probability. Both interpretations are widely used, and choosing between them depends on the context and the kind of the information available. Classic probability is one of the simplest and most intuitive ways to understand chance. It is based on the assumption that all outcomes in an experiment are equally likely. To calculate the probability of an event, we divide the number of favorable outcomes by the total number of possible outcomes. For example, if a bag contains 3 red balls and 7 blue balls, 10 balls in total, the probability of picking a red ball is 3 out of 10 or 0.3. This means there is a 30% chance of drawing a red ball. Classical probability is commonly used in situations like games, cards, dice, and simple random experiments where all the possibilities are known. Bayes' theorem is a fundamental concept in probability that helps us update our beliefs based on new evidence. The general formula is P of A given B is equal to P of B given A into P of A, the whole divided by P of B. Here, P of A given B is called the posterior probability, which tells us the probability of event A happening given that event B has already occurred. P of B given A is the likelihood, the chance of observing event B if A is true. P of A is the prior probability, our initial belief about A before seeing B. P of B is the evidence or total probability of B occurring. When B can happen for multiple reasons like A or not A, we use an expanded version. P of A given B is equal to P of B given A into P of A divided by P of B given A into P of A plus P of B given not A into P of not A. This version helps us evaluate competing explanations for B, like whether a test result is due to a disease or not. Bayes' theorem is widely used in medicine, machine learning, and decision making under uncertainty. Bayes' theorem for multiple causes. When an event like B could be the result of several different causes such as A1, A2, A3 and so on, Bayes' theorem helps us determine which specific cause is most likely given that B has occurred. The formula becomes P of AI given B is equal to P of B given AI into P of AI divided by summation over j P of B given Aj into P of Aj. Here P of Ai given B is the probability that cause Ai is responsible given that we observe B. The numerator is usual product of the likelihood of B given Ai and the prior belief in Ai. The denominator accounts for all possible causes of B by summing the products of likelihood and prior for each Aj. This form is very useful when multiple sources or explanations exist. For example, identifying which of the several machines produced a faulty part or which disease caused a specific symptom. It gives us a way to weigh competing possibilities using evidence and prior knowledge. First problem based on medical diagnosis. There is a disease that affects 1 out of every 100 people. We have a test that can detect the disease correctly 90% of the time when someone is actually sick. But sometimes the test makes mistakes and shows a positive result even if the person is healthy. This happens 5% of the time. Now, if someone takes the test and the result is positive, we want to find out what are the chances that this person really has the disease. To solve this, we use the information about how common the disease is, how accurate the test is for sick people, and how often the test gives false alarms for healthy people. This helps us calculate the true probability that the person is actually sick after testing positive. To find out the chance that a person really has the disease after testing positive, we use something called Bayes' theorem. This theorem helps us combine the chance of testing positive if you have the disease, the chance of having the disease in the first place, and the chance of testing positive even if you don't have the disease. We put these numbers into a formula and do the math, multiply the chance of testing positive when sick by the chance of being sick, then divide that by the total chance of testing positive, which includes both sick and healthy people. When we calculate it, the answer comes out to about 15%. This means that even if someone tests positive, there is only about a 15% chance that they actually have the disease. This shows how important it is to understand test results carefully. Let us say we have an email filter that tries to catch spam emails. Out of all the emails you get, 30% are spam. The filter does a good job. It catches 95% of the spam emails. But it also sometimes makes mistakes and wrongly marks 2% of good emails as spam. Now, if the filter marks an email as spam, what are the chances that the email is really spam? We use Bayes' theorem again, which helps us combine how common spam emails are, how good the filter is at catching spam, and how often it makes mistakes. We apply the given values in the formula. It turns out that there's about 95% chance the email is truly spam. If it's marked as spam by the filter, this shows the filter is quite reliable. Problem 3. Factory defective products. Imagine a factory with two machines making products. Machine A makes 60% of the products, machine B makes 40%. Some products from each machine are defective, 2% from machine A and 5% from machine B. Now, if you pick a product at random and find out it's defective, what is the chance it was made by machine B? To figure this out, we look at how much each machine contributes to the total products and how often each one produces defective items. Using this information, we can calculate the probability that a defective product came from machine B. First, we know that machine A makes 60% of the products and machine B makes 40%. Also, 2% of machine A's products are defective while 5% of machine B's products are defective. Our goal is to find the chance that a defective product actually came from machine B. To do this, we use Bayes' theorem. This formula helps us combine the chance of a product being defective from each machine with how much each machine produces overall. We multiply the defect rates by their production percentages and then use those numbers to find the probability for machine B. After calculating, we find that if a product is defective, there is 62.5% chance it came from machine B. This tells us that machine B's products are more likely to be defective even though it produces fewer products overall. Sampling from distributions. Sampling is when we pick a small group from a large population to study and learn about the whole group. There are different ways to do this. In random sampling, everyone has an equal chance of being picked. In stratified sampling, the population is divided into groups and we take samples from each group. Systematic sampling means choosing every kth person like every 50th customer. Cluster sampling divides the population into clusters and then some clusters are chosen randomly. When we sample, we often use probability distributions like the uniform distribution where every outcome is equally likely, the normal distribution which looks like a bell, and describes many natural measurements, and the binomial distribution, which deals with events that have two outcomes like success or failure. For example, if a company surveys every 50th customer out of 50,000, this is systematic sampling because they pick every K person. Binomial distribution. The binomial distribution helps us find the chance of getting a certain number of successes when there are only two possible results in each trial, like heads or tails in a coin toss. It works when we repeat an experiment a fixed number of times and the chance of success stays the same every time. Also, each trial doesn't affect the others. To calculate the probability of getting exactly a certain number of successes, we use a special formula that counts all the different ways those successes can happen. The formula is P of x equal to k equals nck P of k into 1 minus p power n minus k. This formula includes numbers like how many trials there are, the chance of success and the chance of failure. This helps us understand situations like flipping a coin many times or checking if a product passes or fails a test. Let's look at an example with a coin tossed 5 times. We want to find the chance of getting exactly 3 heads. Since the coin is fair, the chance of heads or tails is the same, 50%. We use the binomial formula to calculate this. First, we figure out how many ways we can get 3 heads out of 5 tosses, which is 10 ways. Then, we multiply this by the chance of getting heads 3 times and tails 2 times. When we do the math, the result is about 31.25%. So there's about 31% chance of getting exactly 3 heads in 5 tosses. In a factory that makes light bulbs, and there is a small chance, 2%, that any bulb could be defective. Now, if we test 10 bulbs, we want to know the chance that exactly 2 of them are defective. We use the binomial distribution formula to find this. First, we calculate how many ways we can choose 2 defective bulbs out of 10, which is 45 ways. Then we multiply this by the chance of 2 bulbs being defective and the other 8 being good. When we do the math, the chance comes out to about 1.53%. So there is a small chance, but real chance that exactly 2 bulbs are defective in a group of 10. Exam passing probability. Let's say a student has 70% chance of passing each exam and they take 4 exams in total. We want to find out the chance that the student passes exactly 3 of these exams. Using the binomial distribution, we first figure out how many ways the student can pass 3 exams out of 4, which in 4 ways. Then we multiply this by the chance of passing 3 exams and failing 1 exam. After doing the calculations, the probability comes to about 41.16%. This means there's a little over a 40% chance that the student will pass exactly 3 out of 4 exams. Normal distribution. The normal distribution is a way to describe data that forms a smooth bell-shaped curve when we look at how often different values happen. It's common in nature, for example. People's heights or test scores usually follow this pattern. The center of the curve is called the mean, which is the average value. The spread or width of the curve depends on the standard deviation, which shows how much the values vary. There's a special version called the standard normal distribution, where the average is 0 and the spread is 1. To understand where a specific value stands, we use a z-score, which tells us how many standard deviations the value is from the mean. This helps us to compare different values and to find the probabilities easily. The formula is P of x is equal to 1 by sigma root 2 pi exponential of minus x minus mu the whole square divided by 2 sigma square. First problem. Finding probabilities with normal distribution. Imagine a factory makes screws that are usually about 5 millimeters wide, but there is some small variation, so the size can be a little bigger or smaller. The average size is 5 millimeter and the size spread out by about 0.1 mm. Now, if we pick one screw at random, we want to know the chance that its diameter is less than 5.05 millimeter. To find this, we first calculate a z-score, which tells us how far 5.05 mm is from the average in terms of the usual spread. The z-score here is 0.5. Using a z-table, we find that the chance of the screw being smaller than 5.05 mm is about 69%. This means most screws are closer to the average size. Problem, we were interested in finding P of z less than 0.5. So this is the z table. From this table, we find that the probability of z corresponding to 0.5 is 0.69146. This is the value that we substituted in the previous problem. Probability between two values. In this problem, we want to find the chance that a student test score is between 60 and 80. We know that the average score is 70 and the scores usually spread out by 10 points. First, we convert 60 and 80 into z-scores, which show how many standard deviation these numbers are from the average. The z-score for 60 is -1 and for 80 it is +1. Using the z-table, we find that the probability of scoring less than 80, that is, probability of z less than 1 is about 0.84. We can see from here, probability of z less than 1 is 0.84. And the probability of scoring less than 60, which is probability of z less than -1, is about 1.58. That is given over here. Probability of z less than -1 is 0.15866. So to find the chance of scoring between 60 and 80, we subtract these. That is 0.84 minus 0.158 gives about 0.68. This means there is roughly a 68% chance the student score falls in that range. The 3 sigma rule. The 3 sigma rule, also called the empirical rule, helps us understand how data spreads in a normal distribution. It says that about 68% of the data points fall within one standard deviation from the mean, 95% fall within 2 standard deviations, and almost all data, about 99.7%, fall within 3 standard deviations. For example, for factory mix batteries with an average life of 800 charge cycles and a standard deviation of 50, then about 68% of the batteries last between 750 and 850 cycles, 95% last between 700 and 900 cycles, and almost all last between 650 and 950 cycles. This rule gives us a quick way to estimate the range where most values lie. In this problem, we use the 3 sigma rule or the empirical rule to find the range within which 99.7% of the mobile phone batteries lifespans fall. The company batteries have an average lifespan of 800 charge cycles and a standard deviation of 50. According to the rule, most of the batteries will last within 3 standard deviations above and below the mean. We calculate this by adding and subtracting 3 times the standard deviation from the mean. So the maximum lifespan is 800 plus 3 times 50, that is 950, and the minimum lifespan is 800 minus 3 times 50, which is 650. Therefore, 99.7% of the batteries will last between 650 and 950 charge cycles.